Hello, my name is James Skelly, and this is my ECG795 final project presentation. This presentation details the design of a high-speed communication system on an 8-layer PCB using an Intel Aria 10 FPGA as a transmitter and a theoretical receiver IC, which consists of high-speed CMOS comparators, D flip-flops, and output buffers. Here we have an overview of the design at the block diagram level. There are three main components to the system. The first is the Aria 10 FPGA, which is modeled by the voltage sources found in Figure 1. The second is the worst-case PCB trace, modeled in LT-SPICE with a 48.5 cm long transmission line model, along with IC package, PCB via, and wire bonding parasitics. The third major component is the receiver IC, which consists of one CMOS comparator, two D flip-flops, a clock generator circuit, which is not pictured in Figure 1, and two output buffers for each of 72 differential signaling pairs in the channel. The total price of the system is $560.90. As we move further in this presentation, a detailed cost analysis will be done using a table. Table 1 contains all of the calculated capacitances, inductances, impedances, and other parameters used to characterize the system. Notice the low reverse crosstalk coefficient in the bottom row of the table and the 0 forward crosstalk coefficient in the row just above it. These low values of crosstalk were obtained by placing adequate space between traces to limit the effects of crosstalk at the PCB level without adding much cost to the system. The cost of implementing crosstalk control would be much greater. Since the design uses bipolar differential signaling, the line impedance can be characterized by the odd mode impedance alone. Let's take a look at the Intel Aria 10 FPGA. The Aria 10 comes packaged in a 484-pin fine-line ball grid array package with a 1 mm pitch. The minimum ball diameter is 0.5 mm and the maximum ball diameter is 0.7 mm. For worst-case analysis, the 0.7 mm diameter is considered when selecting trace width and trace spacing. The Aria 10 costs $410 and is responsible for nearly 80% of the total cost of the system. The chip has 72 LVDS pin pairs for a total of 144 LVDS pins. The device datasheet recommends using a common mode voltage of 1.25 volts when operating with data rates exceeding 700 megabits per second. Since the channel supports data rates of 1 gigabit per second, the system was designed with a common mode voltage of 1.25 volts as recommended. Though the channel is only designed for data rates of 1 gigabit per second, the Aria 10 can support a maximum data rate of 2.1 gigabits per second. The PCB itself is quite large, with an area of 73 square inches. Since the board is 8 layers, the cost is around 75 cents per square inch, making the total cost of the board $54.84. The worst case trace model is shown in Figure 4, modeled by a number of inductors, resistors, and capacitors, and a lossy transmission line. The lossy transmission line is parameterized by the values for resistance, inductance, and capacitance per meter calculated in Table 1. Note that bond wire, BGA ball, and via parasitics are modeled on either side of the lossy transmission line model, since each of these parasitics pertain to both the transmitter and the receiver IC. The receiver IC consists of three main components per link, neglecting the clock generator circuit. The first is the CMOS comparator, adapted from a design found in Dr. R. Jacob Baker's CMOS circuit design textbook. BSIM MOSFET models with a minimum length of 180 nanometers were used in the design of the receiver circuitry. The second stage of the receiver IC is the D flip-flops, where the data is clocked. The schematic for the D flip-flops was also adapted from a design found in Dr. Baker's CMOS textbook. The final stage of the receiver IC, which produces the outputs of the system, is a CMOS output buffer consisting of wide-width cascaded inverters to square up the signals and remove noise introduced in the D flip-flops in the form of clock feed-through. The receiver IC was priced at $33.56 after the price of a similarly sized chip found on DigiKey. Diving deeper into the design of the comparator, we see from Figure 7 that minimum length devices were used to ensure the highest possible speed of performance. The comparator has 4 stages. The first is a differential amplifier with an external bias voltage for preamplification of the differential signals. The second stage is the decision circuit, whose outputs are fed into the third stage, a self-biased differential amplifier for post-amplification after a decision has been made. The final stage is an output buffer, which regenerates differential signals from a single-ended output. The design uses the LVDS signaling standard with a data rate of 1 gigabit per second. Voltage mode bipolar differential signals are used for noise immunity, and a voltage swing of 800 millivolts is selected to limit the effects of independent noise sources. There are two possible signal levels which can be observed in Figure 9. When Vp is 1.45 volts and Vm is 1.05 volts, the output of the receiver is a logic 1. When Vp is 1.05 volts and Vm is 1.45 volts, the output of the receiver is a logic 0. From Figure 8, we see that the signals swing around the common mode voltage and have an ideal bit time of 1 nanosecond. Here we take a look at the timing system which governs the design's operation. Taking a look at Figure 10, we see that single edge-triggered D flip-flops are used to clock the data out on the rising edge of the clock signal. The parameter TD clock in LT-Spice can be modified in simulation so that the rising edge of clock always hits the center of the data bits. The design uses a synchronous timing convention, but the clock generator circuit can be thought to model a digital phase-locked loop which has already locked to the center of the data. We can also observe from the plot of Figure 10 that the clock feed-through noise introduced by the D flip-flops. Later simulation results will show how the output buffers minimize this noise. Figure 10 shows an 8-layer board stack-up and the parameters associated with the stack-up. The PCB is made of FR4, which has a relative permittivity of 4.4. Of the 8 board layers, the 6 middle layers are signal layers. The board was designed in this manner so that the high-speed signals all travel through homogeneous media. The total board thickness is a standard of 1.6 millimeters. Trace width for optimal routing out of the BGA package was chosen to be 4 mils, and trace spacing chosen to be 15 mils. The shortest signal trace on the PCB is 40 centimeters long, while the longest is 48.5 centimeters long. Figure 11 shows the eye diagram at the input of the comparator. Figure 12 shows a transient analysis of the signals at the input of the comparator. These signals are quite noisy, and the effects of the modeled parasitics are observable. Reflections are apparent due to the mismatched termination resistor, which at worst is mismatched by 20%. We can also take a closer look at Figure 12 to observe attenuation modeled by the lossy transmission line. The signals are supposed to swing between 1.45 volts and 1.05 volts, but we can see that they swing around roughly 1.42 volts down to around 1.08 volts. Table 2 shows the noise budget for the system. The voltage swing of 800 millivolts, as mentioned previously, limits the effects of the independent noise sources. Cutting this value in half gives us our gross margin of 400 millivolts, and subtracting all bounded noise from the gross margin yields our net margin of 146 millivolts. Power supply noise combined with other sources of probabilistic noise result in a total Gaussian noise of 15 millivolts RMS. The system has a voltage signal-to-noise ratio of 9.73 and can probabilistically perform reliably without an error for over 11,000 years. Figure 13 shows a timing diagram for the system, highlighting the ideal bit time, the rise and fall times under worst-case conditions, and the aperture time. The aperture time of the signal is equal to the ideal bit time minus the sum of the rise or fall time and the total timing uncertainty. Sources of timing uncertainty and the sum total of those sources are found in the table on the slide to follow. Observe Table 3, the system timing budget. All sources of skew and jitter are listed in the table. The trace delay is also listed, but the delay through the comparator, flip-flops, and output buffers is left out of this table. The total delay from input to output of the system is around 3.75 nanoseconds and can be observed in the TDR and TDT waveforms in the results section. The aperture time of 555 picoseconds was obtained by subtracting the sum of total uncertainty and clock rise time from the ideal bit time of 1 nanosecond. The analysis of power consumption was split into two main portions, the transmitter side of the circuit and the receiver side of the circuit. The analysis was performed by using SPICE to find the average power per cycle supplied by the transmitter voltage sources and the average power per cycle supplied by VDD to the receiver circuitry and summing these two averages. Figure 14 shows the plot of voltage, current, and power when sending alternating ones and zeros down the channel at 1 gigabit per second. The magnitude of average power of one line was obtained and is seen in figure 15 as 1.96 milliwatts. Since there are two lines per link, the transmitter side of each link supplies 3.92 milliwatts of power per cycle on average. Figure 16 shows the plot of voltage, current, and power supplied by VDD to the receiver circuitry. The magnitude of average power dissipated in one link's receiver circuitry is obtained in figure 17 as 8.66 milliwatts. The total power consumed by one link is the sum of these two values, or 12.58 milliwatts per link on average. Table 4 shows all of the average power dissipation values relevant to the analysis of the system's overall power consumption. The sum of the power dissipated by the comparator, the D flip-flops, the clock generator circuit, and the output buffers yields the total power supplied by VDD to each link. Since there are 72 links in the system, the total average power dissipated by one link multiplied by 72 yields the total average power dissipated by the entire system, or 905.8 milliwatts on average. Table 5 shows a complete cost analysis of the system. The PCB costs $54.84. The ARIA 10 FPGA costs $410 even. The receiver IC is estimated to cost $33.56 after a microcontroller with a 160-pin BGA package on DigiKey, and the terminating resistors cost $62.50 for a full reel and can only be purchased with a minimum quantity of 5,000 from DigiKey. The total cost of the system is $560.90, and the cost per link is the total divided by 72, or $7.79 per link. Here we observe the performance of the system. The top plot shows the LVDS signals on the ARIA 10 before leaving the chip. We see the clean square waveform swinging from 1.65 volts down to 0.85 volts. The next plot down shows the noisy delayed signals at the end of the PCB trace before entering the comparator. The third plot shows the signals after they are clocked by the D flip-flops and clock feed-through noise is introduced. This is observed as the little spikes on the waveforms every half a nanosecond or so, and is caused by rising and falling edges of the clock signal feeding through parasitic capacitors straight to the output. The final plot at the bottom of figure 18 shows the outputs of the output buffers, which are square waves with no feed-through and have reliably detected the correct bit stream with a delay of just under 4 nanoseconds. The eye diagrams at these same nodes can also be observed. We see that the first plot shows a wide open eye with no noise whatsoever. The second plot shows a noisy eye that is starting to close a bit due to noise from the PCB trace model. The third plot shows a clean eye diagram with slight effects from reflections and feed-through after being clocked, the D flip-flop outputs. And the final plot shows the eye diagram at the output of the output buffers with no noise and full logic levels. The TDR and TDT waveforms can be observed in figure 22. We see the effects of reflections and a round-trip delay of around 7.5 nanoseconds from the lossy transmission line model. Voltage peaks stem from parasitic inductances, while valleys are a result of parasitic capacitances. The pulse source used to generate this waveform has an amplitude of 1 volt and a rise time of 20 picoseconds. The fast rise time causes the noise seen in figure 22. Future work on this design consists of improvements to both the line model and the system itself. A higher attenuation, which is much more likely in real life to occur, can be modeled on the line using a voltage-controlled voltage source. Modifications to the system include D flip-flops instead of inverters to regenerate differential signals at the comparator output. The single-ended output can be fed into the D flip-flop clock inputs, and one D flip-flop data input could be tied high while the other is tied low. This would produce differential signals and eliminate the delay introduced by the inverter in the current design. The final improvement is to design a digital PLL for the system rather than modeling one with an ideal clock generator circuit. In summary, the system operates reliably at a data rate of 1 gigabit per second with a total cost of $560.90. A total average power consumption of 905.6 milliwatts for the entire system. From an ideal bit width of 1 nanosecond, we are left with an aperture time of 555 picoseconds due to timing uncertainty and a worst case rise time of 130 picoseconds per the transceiver speed grade given in the ARIA 10 datasheet. Here are a list of the references for this project, and thank you so much for listening.